In today's video, we're going to start our discussion on the normal distribution. The normal distribution is a particular type of experiment that we're going to be looking at, and these experiments will take on this distribution where if you draw their histogram, you will get this curve shape out of the histogram. There are lots of different examples in the real world of normal distribution. So different experiments that may have a histogram that has this normal distribution would be things like if I looked at the height of children across the US. Okay, I've taken a whole population of data and I look at children's heights at a certain age, whatever that age might be, and you will see that you will get this type of curve from your histogram. Okay. So when you go ahead and you figure out what each of your outcomes are, so your outcomes will be along this x-axis here, and then you will find when you go ahead and draw that histogram with each of the bars representing the frequencies for each of these outcomes, you will see that for a whole population it should take on this kind of bell-shaped curve. Okay, that will happen for a lot of different populations, a lot of different experiments on populations within real-world problems. So like I said, heights of children is one. If I look at the weight of children, that's another one. If I look at the IQ of people across America, okay, that would be another example of something that when I drew the histogram, it would have this like bell-shaped curve to that histogram. This is called the normal distribution, okay? Any experiment that will then take on this curve is said to have normally distributed outcomes. Okay, so when you've observed what the outcomes are, you've figured out the frequencies, you go ahead and draw the histogram, and then you find that they follow along this bell-shaped curve, then those outcomes are said to be normally distributed. Whenever you look at a particular experiment that has normally distributed outcomes, and you get this curve, it's always going to be symmetric. That's the first thing with normal distribution. It's symmetric. And it's symmetric about this central line here. Okay. Now, from histograms, we know that whatever outcome has this central bar, that will be the median. Okay, we already know that because we know that our data points have to be symmetric about that middle point whenever we look at the median. Okay. We also know that the mean is a balance point with histograms. And because this is symmetric, we know that this middle point must also be the mean. Okay. So from histograms, like I said, we know that it's the median, but because the mean is a balance point, we know that this must also be the mean of our population. So whatever your central line that this curve is symmetric about is not only your median, it's also the mean. And it is also actually, if you have done this before, it's also the mode, because it's going to be the most common point, the most frequent outcome. So for normal distribution, you will find that the mean equals the median equals the mode. But the main thing that I want to look at here is the mean. Okay, so that central line, whatever outcome is in the middle that this curve is centered around, is the mean. Okay, so bear that in mind whenever we have these normal distribution curves. Now looking at probabilities. Okay, we did this before with histograms. If we wanted to know the probability of a certain set of outcomes, okay, all we did was we took this histogram where we had the outcomes on that x-axis, and on the y-axis, if we drew a y-axis here, wherever the y-axis might be, on the y-axis we had all of the probabilities of each of those outcomes, okay? And then you drew each of those rectangles to represent whatever the probabilities of each of the outcomes were. Therefore, for a normal distribution curve, if I want to find the probability of being between two outcomes, we'll call them outcomes A and B. I want the probability of picking an outcome or picking a person that will have a property of a certain outcome to be between A and B. All I have to do is to find the area of the curve, area underneath the curve between A and B. So if I want the probability that an outcome is between two values A and B on my x-axis, then I find the area under the curve between A and B. As you would expect, and as you can kind of figure out from histograms, if each of these outcomes has a certain probability, and like we've just said here, that the probability of being between two outcomes is going to be the area under the curve between those 2 points, the area under the whole curve, so this yellow part here, is going to be 1. Because all of your outcomes are on your x-axis, okay? So the probability of landing somewhere underneath that curve is going to be 1. Okay, because you have a 100% chance of having some outcome. Okay, so if I pick a child in the US of, let's say, age 10, okay, and I have this normal distribution curve here that looks at the weights of 10-year-olds, okay, that child will have some outcome on that curve. Okay, so there is a 100% chance of picking a child that has some weight on this curve, okay? So the probability of having some outcome is going to be the area under the whole curve, which is 1, because you have a 100% chance of having one of the outcomes. And like I said, the probability of being between two outcomes, A and B, is going to be the area under the curve between those 2 points. Okay. Next, I want to bring in the standard deviation and variance that we looked at in our last video. So again, let's draw out a normal distribution curve. You can have different curves. I'm going to actually draw a slightly different one here, which is going to be much flatter and wider like that, okay? Both of these curves, I know that they're not drawn incredibly accurately, but both of them, let's say, are centered around, we'll call them the same mean. Let's say that the mean equals 5 for whatever this data set is. Okay? Both of these curves are centered around a mean which equals 5. But you'll notice that this curve is much sharper, okay, and goes much taller. This curve is much more spread out, much flatter, and doesn't go as high. Okay. What's the difference? Well, you can kind of figure out here from your data points. On this particular curve, all of your data points are much closer to the mean. Okay, they're much less spread out. You have this much sharper hump that is closer to the mean. On this curve here, your data points are much more spread out. There's a lot more data points that are further away from the mean. Okay? Going back to our definition of variance and standard deviation, which look at how spread out your outcomes are from the mean, we can tell that this particular curve that is sharper is going to have a much smaller variance and much smaller standard deviation because your points are much closer to the mean. For this particular data set, again, you've got the same mean, but your data points are a lot more spread out from the mean, telling me I must have a much larger variance and standard deviation. So for this curve, I've got a smaller variance and standard deviation as data points are much closer to the mean. Which must mean that they're less spread out. Okay. For this curve, again, same mean as the last one, but I've got a larger variance and standard deviation. And points are more spread out. Okay. So you've got a lot more data points that aren't as close to the mean for this particular curve. Okay. What you tend to find is that roughly 2/3 of your data points will be within one standard deviation of the mean. Okay, so if I figure out that here, again, this is not accurate, but let's say I figured out that my standard deviation here was 2. Okay, if I take one standard deviation either side of the mean, so I'm going down to 3 and up to 7 if your standard deviation was 2. I should find for one of these curves that roughly 2/3 of my data points land within one standard deviation of the mean. So if I go one standard deviation below and one standard deviation above, I should find that roughly 2/3 of my data points land in there. Same thing happens here, but we have a much more spread out data set here. So here you would expect to find a larger standard deviation. So let's say that here your standard deviation was 4. Okay. So again, if I go one standard deviation either side of the mean, in this case I would have between 1 and 9 if my standard deviation was 4, I would still have 2/3 roughly of my data points land within one standard deviation of the mean. Okay, it's not exactly 2/3, but it should be roughly 2/3. So that's kind of a good indication whenever you look at one of these problems as to how your data is spread out. Okay, and roughly what your standard deviation might be. So if you're given one of these curves and they ask you to approximate what the standard deviation might be, by looking at the curve you could probably make a pretty decent guess as to what the standard deviation might be by taking roughly 2/3 of the curve in the middle and looking at what that standard deviation might be, such that 2/3 of your data points are within one standard deviation of the mean. We're going to look more at this next part in the next video, but what I want to look at specifically is something called the standard normal curve. Or the standard normal distribution. Okay. For the standard normal distribution, okay, standard normal distribution is a curve that has a mean of 0 and a standard deviation of 1. That means that when I draw out my curve, like this, it's going to be centered around a mean of 0. And like we said, roughly 2/3 of your data points for a normal distribution should be within one standard deviation of the mean. So if I take roughly 2/3 of my data points they should be between -1 and 1. Okay. This is called the standard normal distribution. So any data set that has a mean of 0 and a standard deviation of 1 is called the standard normal distribution. Now, real world, you're probably not going to have many data sets that actually fit this description. However, the reason that we use it is because it makes calculations a lot easier, for one, and especially when calculators weren't a thing, and I'll tell you why in a second, it made it much easier. But also, we can take any data set that has this normal distribution and transform it into the standard normal distribution. That's what we're going to look at in our next video. So we're not going to do that right now. But I'm going to look at the standard normal distribution because I know it does make calculations a lot easier. And I know that any data set that is normally distributed, so it does follow a curve, it may look flat like this, it may look sharper like this, it can have whatever mean and whatever standard deviation, but I can always transform it to have a mean of 0 and a standard deviation of 1 to make these calculations easier. Now, nowadays, it's not as big a deal because we use calculators. Not that long ago, within the last 10 years and before that, statistics tables were used in order to find probabilities using normal distribution. They're pretty easy to understand once you get the hang of it. They're just not as easy as using a calculator. So what we actually do here is I'm going to show you how to do all these calculations using a calculator. I'm going to start out with the standard normal distribution and I will teach you how to transform into the standard normal distribution. But nowadays you can pretty much do all of this on a calculator anyway, so it's not as big a deal, but it's still something to be aware of. Okay. What are we going to be looking at with the standard normal distribution? Well, let me come back to here where I was looking at probabilities. Okay. We were looking at the between A and B. What's the probability that I have an outcome that lands between A and B? That's the kind of problem that we are going to be looking at here. But I'm first going to look at this in terms of the standard normal distribution. Okay, so I'm going to look at what's the probability that I land between two data points, given that my mean is 0 and my standard deviation is 1. Okay, I'm also going to look at problems where I look at what's the probability that my outcome is less than a particular value or greater than a particular value. Okay, it's going to work exactly the same. It's going to be what's the area under the curve to the left or the right of that point, whether I'm looking at less than or greater than. So it's still going to be the area under the curve, but we want to make sure that number one, we are shading the right region of the curve so that we know that what we're looking at, but then we are going to use calculators just because they make it a lot easier than using statistics tables. Okay. So here I'm going to look at an example. I'm going to do several different ones here and I'm going to tell you how to access this on your calculator rather than using statistics tables. So we're going to be determining areas of regions and hence the probabilities of outcomes under the standard normal curve. So let's say, and I'm going to do a piece of notation here as well. What's the probability? I'm going to use Z here, and I'll tell you why in a second, that Z is less than or equal to negative 0.5. Okay. I'll tell you about Z in a second because that's a notational thing. But in terms of, again, we're doing the standard normal curve here. I'm not looking at anything else other than a mean of 0 and a standard deviation of 1. So if my mean of 0 is here my standard deviation of 1 means that -1 would be roughly there in order to have 2/3 of my data points in the middle. So -0.5 is roughly here. So I'm looking at what's the probability that I have an outcome that is less than or equal to -0.5. So I'm looking at the area under the curve to the left of -0.5. Okay, because I'm looking at what's the probability that I'm less than or equal to that value. So it's the area under the curve to the left of -0.5. Why are we using z? Just as a notational thing here, whenever we talk about the standard normal curve, so any data set that has a mean of 0, standard deviation of 1, we use z. So if you ever see them use the probability that z is less than, greater than, between two values, if you ever see z in one of these problems, automatically you should think of mean of 0, standard deviation of 1. If you see x, it means we're going to be using a different mean and different standard deviation. So it's not going to be the standard normal curve. It will still be a normal curve, but it's not going to be standard normal for this chapter. Whenever you see z for anything in 7.6, I want you to think mean of 0, standard deviation of 1. Even if they don't tell you that that's what the mean and standard deviation is, if we use z, it means standard normal distribution. Okay? So what do we do here? Well, you can use statistics tables, like I said, and you would be looking at the area under the curve to the left of -0.5. Okay? You could use the statistics table if you wanted to. They are in the back of the textbook. However, I would not recommend it. It's not the easiest way of doing this. If you go to your calculator and you click on the second button, so the second one is the blue button in the top left corner, second, and where it says vars, okay, so it's got the distribution above it, so second and vars, you should come up with a bunch of different distributions. I want you to go down to the second option, which is normal CDF. Okay, so you've done second and vars and go down to the second option, which is normal CDF. It's going to ask you for 4 pieces of information here. This is also why, now that we have calculators, standard normal distribution isn't as big of a thing anymore, because we can actually change our mean and standard deviation. It's going to ask you for a lower limit, an upper limit, and then the mean and the standard deviation. Because we are looking at the probability that z is less than -0.5, okay, we know that our upper limit, so the largest value that we're interested in, is -0.5. We don't actually have a lower limit. This thing's going to go all the way down to -infinity. It's pretty much an asymptote here, okay? You're never actually going to hit the x-axis because there's always going to be some outlier that's all the way down the other end, okay? So you're never actually going to hit the x-axis. So we have to account for every single outlier that's going to go all the way down to -infinity. Similarly, if I was looking at a greater than or equal to problem, I would have to account for everything that goes up to +infinity. So all I want you to do in this case, whenever you end up with one of these problems where it's open-ended on one end, so we've got an open lower limit here because we've got to go all the way down to -infinity. For your lower limit, I want you to type in a very large negative number. If we were looking for an upper limit that was not specified, I want you to type in a very large positive number. Okay? So if you type in a very large negative number into your lower limit, you can do something like -1 million, -10 million, whatever you want to do. And then you've got an upper limit of -0.5. Now we're looking at standard normal distribution. So I've got a mean of 0 and a standard deviation of 1. And then I want you to hit enter, and it should solve it for you. So in this case, we get 0.3085. So we've done normal CDF, with a very large negative lower limit. So like I said, I think I did negative 1,000,000. And then your upper limit is negative 0.5. Your mean is 0, your standard deviation is 1, and it should come out to 0.3085. And there's some more at the end if you had to go to more decimal places. Okay. You would get the same value if you did this on statistical tables. Okay, so it doesn't matter which way you do this. But like I said, because we have an open-ended problem here, where I'm looking at less than or equal to some number, I've got my upper limit. I don't have a lower limit for a calculator, so I just type in a very large negative number because I know that this is going to go all the way down to negative infinity. Similarly, if I was looking for an upper limit for a problem, if I had a greater than or equal to problem, I would type in a very large positive number. Okay. So this is the answer to that particular problem. Let's go ahead and do another one. So this time I'm going to look at what's the probability that z is between 1 and 2. So again, I would draw this out. I would always recommend drawing these just so that you know what you're looking at. I've got my mean of 0 in the middle. Then I've got a standard deviation of 1. So I know 1's roughly around there in order to have 2/3 of my data points between negative 1 and 1. And then 2 would be probably roughly here. So I want the probability being between 1 and 2. Again, I've got a mean of 0, standard deviation of 1. You're going to do the same thing again. I want you to go to second and vars and the second option down of normal CDF. So we're looking at normal CDF, and this time I have both a lower and upper bound. So your lower bound is 1, your upper bound is 2. So I've got a lower bound of 1, an upper bound of 2, and my mean and standard deviation are 0 and 1. And you should find that you come out with 0.1359. Okay. If you have an older style TI-84 calculator or a TI-83, you may find that you actually have to type it in like this. So it's always going to be lower bound, upper bound, mean, standard deviation in that order if your calculator does ask you to type it in that way. Most of the time it will bring up a menu with lower, upper, mean, standard deviation. But if you do have to type it in like this, it's always the lower bound, then the upper bound, then the mean, then the standard deviation. Okay. And finally, we'll do an upper limit where there is no upper limit type of problem. So we'll do the probability that z is going to be greater than or equal to 1.5. Okay. Again, we're going to draw this out like this. Your mean of 0 is going to be in the middle. Your standard deviation of 1 would be roughly there, which tells me 1.5 would probably be around here. And we're looking at what's the probability that z is greater than or equal to that. So same thing again, second and vars go down to normal CDF. So we're looking at normal CDF with a lower bound of 1.5. This time I have no upper bound, so I'm going to type in a very large positive number to be my upper bound. So in this case, I'll go with 1,000,000 as my upper bound. And then my mean is still 0, standard deviation of 1. I know I'm looking at standard normal distribution, so I'm not looking at any other mean or standard deviation. If you do that, you should find that you get 0.0668. Okay. So all of these are just probabilities. Okay, so you've got a probability of roughly 6.68% that you will be greater than 1.5 if you have a mean of 0 and a standard deviation of 1. Okay. Another way of phrasing this problem is saying what's the probability that I'm greater than 1.5 standard deviations above the mean. Okay. This only works because your mean is 0 and your standard deviation is 1. So here 1.5 times 1 is 1.5. So you still get the, in this case, just for standard normal distribution. This is also the same thing as saying what's the probability of being greater than or equal to 1.5 standard deviations above the mean. Just because your mean is 0 and your standard deviation is 1. Okay, that works. Here you would be looking at what's the probability that I'm between 1 and 2 standard deviations above the mean. And you could also say here, what's the probability that I am less than 0.5 standard deviations below the mean. Okay, so for these standard normal distribution problems, you can also phrase it in that way. In the next video, what I'm going to look at is transforming some of these other normal distribution problems that have a different mean and a different standard deviation into the standard normal distribution. I'm also going to look at the inverse norm, where you are given the area and you have to find what outcomes you are between, or what outcome you're less than or greater than. So we're actually going to do the inverse of this as well. And then that should be the end of the normal distribution, but we will look at that next time.